PC and PL, those are going to equal. So all those things are going to happen at our resonating frequency. Those are all things that we already know even before we even start doing our calculations. So let's go ahead and let's do our calculations then. So a lot of times all we ever doing are just approximations. We just kind of have, we just kind of, if we're looking at our, voltage of our capacitor and our voltage of our inductor, and they're both equal, then we know that we're probably at our resonating frequency. All right, so what would be my first step then? I'm going to actually do the actual calculations, and what would be my first step that I'd want to do?
Get your X of C and your X of L.
Yep, we can calculate out that, but before we calculate out X of C and X of L, we're going to need to know what?
Oh, the frequency.
We're going to need to know the frequency. So this is going to be our first step. We're going to calculate out what our frequency is going to be. So let's calculate out what that frequency would be.
See, I got that yesterday. Did you get 12.99?
Huh?
12.99? $12.99.
What was it?
12.99 kilohertz.
12.99 kilohertz. Okay, so everyone get that then? Everyone agree with that? All right. And we do know that our angle of our frequency is going to be at 0 degrees. All right, now we can go ahead and calculate out our X of L and our X of C. If there's something that you don't know how to calculate out or how to use your calculator, this would be a good time to stop and ask, and especially if you don't know how to use your exponent key or how to use your memory. So once you got your frequency, once you got your calculated out your frequency, then you should have put that automatically in the memory right away.
Oh crap. X of C is 1.225 kilo ohms.
1.225 kilo ohms. And once we know X of C, then we're going to know X of L, so we can go ahead and fill that one in. All right. Okay, so then what would be our next step then?
X of T?
Yep, we can calculate out our X of T, and we know that when we can algebraically just add those up, knowing that X of C is always going to be a negative number, X of L is going to be our positive number. Just as an imaginary, what we call just our imaginary numbers there, we would treat X of C as a negative number, but when we write it down, we don't put the negatives in there. So X of T then is going to equal what?
0.
0. And that's ohms. All right, then what would be our next step? So when I'm doing RLC circuits, I always stick with all the impedances and resistances first. So that's what I would stay with so far.
Should we do ZT next?
ZT then?
Or, well, we can't because we got to get the R stuff first.
Need to get what?
R?
Yeah, we need to get R first. Yep, so R is going to equal what?
77 ohms.
77 ohms. Then once we know R, we're going to know ZT, and ZT is going to equal what?
77.
Yep, they're 77 ohms. Okay? think we got all our impedances all taken care of and all our resistance. So that would be my next step.
Current?
So now we can calculate out our current. Just using our basic Ohm's law. So V over R will get us our current, or V
Over ZT?
V over our ZT.
.299 milliamps AC.
Milliamps AC. Good, I'm using the units, so. Okay, everyone agree with that then? All right. Now, once we know that we got our total current, then we know what with our current.
It's constant.
It's constant, so we know that that's going to be going across all our components.
You said what was the IT?
1.299 milliamps.
Got 1.22.
It's 1.299.
1.29.
2.29.
Yeah.
All right. Then what's going to be our next step then?
Power? Oh, I suppose we should solve for voltage on each.
Yeah, I would do the voltage first.
Okay.
Yeah, but you could do power. You actually do have enough information to do power. It'd be I squared R. You could calculate all your power because you do know I and you do know R, the resistance, so you can use the formula I squared R. But yeah, most logically though, we want to stick with our voltage.
VC is 1.591 volts AC.
Okay, 1.591.
Yep.
And we know that that's going to be the same as VL then, 1.591 volts AC. So again, a lot larger voltage than what we have for our source voltage. Okay, then
Resistor is 57.76 kilovolts AC.
57.6
76.
millivolts AC. Hey, everyone agree with that then?
You sure about that one? Did you add?
Everyone else agree with that number? Or
0.05 millivolts AC.
Oh, wow. What did I do wrong?
It's just the current times resistance.
Yeah, current times of resistance. And what did you get, Ryan?
Oh, macro.
61.05 volts.
Volts AC.
I agree with them.
All right. Yeah.
No, I don't.
Who agrees with Ryan and who agrees with?
Oh, I agree with them.
All right. Well, once we put you on the spot there, huh?
I still don't agree with them. What the heck am I doing wrong? 1.299 milliamps.
Yeah, I'm sticking with Ryan.
What am I?
I'm on Ryan's team.
Well,
I must be putting something wrong with my calculator. I'm so not getting it.
7 times point.
Hold on.
1.299.
So you're taking 47 ohms.
Mm-hmm. Oh,
47
no.
ohms, yeah. 47 ohms times 1.299.
Oh, I put 229.
Oh, jeez. All right, yeah, so you should get 61.05 milliamps, millivolts AC. All right. Now we can. Now the only thing we got left now is our power. So let's go ahead and let's calculate out our power.
Power total is VAR, right? Or bar? Or
Yeah. So power total is VA, volts amps.
and then the capacitor and inductance is bar.
Bar, yeah, volts amps reactance. Yep.
.067 millivar.
Okay, so that's our total.
As our capacitor, our total is
So give me your capacitor. What did you get for your capacitor?
2.067 millivar.
Okay. And then we know the power of the capacitor, then we know the power of the inductor. Okay, everyone agree with that then? For the power of the capacitor and the inductor? Okay. Then what did you get for your power total?
129.9 milliVA.
129.9
9. Yep.
milli VA. Okay. And then power of our resistor then?
.30 micro watts.
Watts. Good. True power. That's actually going to dissipate heat as we're going across the resistor, or so this resistor also could be an antenna, so that could be 79.30 microwatts as an electromagnetic field also. Not necessarily just always heat, but it can be also our electromagnetic field. All right, so now we have all our basic stuff. Now we're going to go and take a look at our stuff that has to do with our frequency response curve. So how do we calculate out Q?
X of L divided by R.
Yeah, our X of L divided by R.
Is that by R total or just plain old R? Or
Yep, your R total. Yep. Yeah, because it doesn't. The circuit doesn't know where all that resistance is. It just knows that's the total amount of resistance.
$15.91.
15.9. And this is this quality is it's actually a ratio of our power. So if you look in the book there, they actually tell you that it's the ratio of your power and stuff like that. But then once you reduce it down, it ends up equaling X of L over RT. But it's just a ratio. It's just going to tell us the quality of our circuit. All right. Then once we get our quality of our circuit, then we can calculate out what our bandwidth is. And how do we calculate our bandwidth?
Frequency divided by quality.
Yeah, our frequency divided by our quality.
How did you calculate out the power total? Because I get 129.9 microvolts.
That's what I did.
Oh, I made just.
Okay, gotcha.
I got it. Yep. Micro VAs. Yep, good catch. Yep. You see anything like that?
I'm curious, if you do your rounding and your X of C and X of L don't, like one's like say 1.224, like on a quiz, do you want them to be identical?
Yeah, if
you can. If you do actually put the actual numbers that you actually end up calculating out, that's fine.
But then,
if you do this, and it's not quite exactly right, this I'd be almost just as impressed with, because I know that that X of L should equal X of C.
Yeah.
Or PC should equal PL and stuff like that. So.
Because if you don't match them that way, your X of, because I did that yesterday, I was working on this one at home. Your X of T comes out at -1.
No, I guess so you rounded and it gave you.
Yeah, because if you round out.
If you put your numbers in your calculator, and that's what I was saying, if you start using your numbers in your memory, then those numbers will come out exactly right. It's just that what you're doing is that you're ending up using your rounded numbers. But if you didn't use your rounded numbers and you used your numbers in your calculators using the memory, it did come out exactly.
Oh, okay.
Yep.
Okay.
Yep. So if you could bring it out to 25 digits, those numbers would, they would always come out just perfect.
Okay.
Yep, but it's our problem because of our rounding, and we really see that on RLC circuits and stuff like that.
Well,
we're talking such small numbers and stuff like that.
And then I think with the power total, it actually comes out at like 129.949.
Yeah.
If you round that next digit, it technically comes a 5. So would you round up or not?
So it comes up, so it's 1.2.
No, 129.949. I think that's what it was. It's either that or the frequency.
So let's see. This one here.
Yeah.
Our power total.
Yeah.
So 129 point.
It's either the
9.
frequency or the.
So then it was 4.9.
Yeah.
Yeah. So technically, if you went out to the. Yeah. So.
Would that be acceptable on a quiz or not?
Well, no, because we always look at 4 digits.
Okay.
And we look at this one, and we're rounding 4 digits, and we look at this one. But yeah, if you were really wanting to get
specific.
This is, I don't know if you ever remember at the very beginning of class, I was telling you about the round even rule.
Oh, yeah.
Yep. This is, if we were really doing it, if we were doing it outside of school here, and we did the round even rule, we'd follow a certain amount of rules to how we'd end up rounding this properly.
Okay.
So this round even rule, since this number is an even, we would probably round that one up. I'd have to take a look again and back on my round even rule. But if you do if you do rounding and stuff in Excel and stuff like that, the Excel uses the round even rule because the degree of error will be a lot less if you use that round even rule. Yeah. But for our practical, for just knowing to learn the theory of it and stuff, we don't monkey around with doing the round even rule. We just stick with that 4-digit rule. Yeah, but there is a certain rule that you do want to follow when you're doing the rounding. All right, so then our bandwidth then is going to equal to what?
816.47. Oh crap! I didn't write down if that's kilohertz or not.
That's 816.5 hertz.
816.5 hertz. Okay, everyone get that then?
Yeah.
All right. All right, then, so then to figure out our lower frequency cutoff, then all we have to do is divide that, our bandwidth, divide that by 2, and then subtract it from our total resonating frequency, and then we just add the other half to the resonating frequency, and that'll give us our upper cutoff. So what do we get for our lower frequency cutoff?
12.58 kilohertz.
12.58 kilohertz. Okay, and then our upper frequency cutoff?
13.4 kilohertz.
All right. Pretty straightforward once you understand the steps and the process and stuff. So then let me put this one in our, let me put the values in the spreadsheet, then we can look at the frequency response curve.
Is there ever an application where you don't want to be running at your resonant frequency?
No.
Or you always want to tune it into your resonant?
Yeah, if you're always going to want it. Yeah, if that's...
So you come across a circuit, you just solve for the resonating frequency and then adjust?
Right.
Okay.
Yeah. Yeah, because it's, that's the whole... Because anything else, all I can show you here.
Well, I couldn't think of any offhand if I had.
So then... So if I put these numbers into my spreadsheet here, you can see then we end up with the same resonating frequency. You got 12.99 kilohertz. I had a bandwidth of 817 hertz. My lower frequency cutoff was 12.5 something. I can't quite read it.
12.5.
And then 13 point, what was it? 5.8. And then 13.4 kilohertz for our upper frequency cutoff. And my half power would be at 0.707 of my voltage source. But since we have such a large amount of resistance in our windings, our maximum voltage coming out of our resistor is going to be, what did we calculate out for our output?
61.05 millivoltage.
Yeah, so that would be our maximum. That would be our maximum voltage coming out of our thing. So we'd have to make our, so it's not going to be at 70.7% of our voltage source because of the resistance of our winding of our inductor. So we'd have to accommodate for that when we go into our next or go into our amplifier stage. The thing I don't like about open office is that I have to have all my so yeah, when you're graphing this stuff, sometimes it's hard to graph, but when you're graphing, I'll show you on the very bottom. One thing I like about open office is that these last 3 rows that I calculate out, I'm calculating out my lower frequency cutoff, my resonating frequency cutoff, and then my upper frequency cutoff. And I put those last 3 rows into my spreadsheet so that no matter where my resonating frequency is, I always end up recalculating that out right at the very bottom. And then I recalculate it out because my chances of me when I'm doing my numbers here, zoom in so you can see it. So you can see, like, here's my frequency, I'm going 10, 20, so my chances of me actually hitting my resonating frequency is never going to be possible. So when I end up plotting out my graph, then I'm going to get a weird looking graph because I'm not actually plotting out the 3 critical points that I want to see graphed out. And that's my resonating frequency, my lower frequency cutoff, and my upper frequency cutoff. So one thing I like about open office is that I can put this right on the bottom, and it doesn't matter where it lies inside the spreadsheet. It's going to go ahead and I can tell it to graph it according to my frequency. So it'll automatically reorganize my spreadsheet and plot it out in the right direction. Where Excel won't do that. Let's see if I can show you real quick. That's kind of a handy little tool that you can. So here's what Excel would look like, because you can't do this in Excel, but there's one that says sort by X values. That's my frequency. So if I click OK and say OK, here's how Excel's would graph it out. That's what happens, because what it does is it does the whole top part of that spreadsheet, then it comes back over, and then it does my last 3 rows. And that's the only way I can do it in Excel, and so my Excel never displays it properly. So that's why I like using Open Office, because Open Office I can go ahead and regraph out my, according to my X and Y values, or my X values. Now if I put it back and say sort by the X values, then I get a nice looking graph. But I want to have that because I need to have those 3 points on the very bottom of my Excel sheet so that I can hit these particular spots. If I didn't have those 3 data points in there, I'm only got what do we calculate on 816 hertz for our bandwidth, right? So if I don't hit that bandwidth, and if I don't hit if I don't plot that resonating frequency, my bandwidths, my upper and lower frequency cutoffs, I can miss that totally, completely in my spreadsheet. I wouldn't even see this thing spike because it only happens so quick. So if I got a number above it and a number below it, outside that range, all I'm going to see is this, because I'm going to miss those points. So I have to plot out. So when I'm plotting out my certain things, like for resonating frequencies, I've got to make sure that I'm plotting out exactly what my resonating frequency is, and then I have 2 data points here, and that's my bandwidth. So my bandwidth is right in that area there. So let me zoom in on that. Yeah, so here's my So here's my bandwidth. So you can see I have a pretty narrow bandwidth. I'm only at 816 hertz. That's the difference between this one and this one. And if I should be able to click on it. But let's take out of here. Find my. So then you can see that when I actually ended up doing the calculations on it, then they were both pretty close to my 45 degrees. Yep. So again, you can kind of see, here's my X of C, that's going to be, or my VC, that's going to be equal to my source voltage. My VL is going to be very low, and those two are just going to go along, and nothing happens to them until all of a sudden I get right to my resonating frequency, and then all of a sudden VL and VC are both going to spike up really high, and then they're going to both start coming down right on my other side of my bandwidth, and they're going to start to drop. Then VL is going to stay high, and then VC is going to stay low for the rest of any of those other frequencies. So, yeah, so if I were to do anything outside of that resonating frequency, you can see I'm just not going to get any change. Okay? So the only time that this circuit really becomes active is right at my resonating frequency. And then my VL and my VC are going to cancel each other out. Those two are going to act like a short going across my circuit. There's not going to be any voltage across either one. They're going to act like a short. And then so all my voltage goes across my resistance of my circuit. And then since I have such a large amount of resistance across my windings of my transformer, that's almost, or my inductor, I'm going to lose about almost half of my voltage across my resistor, because a lot of it's dropping across that inductor because of the resistance of that winding was 30 ohms compared to 47 ohms. So I would just have to make sure that my amplifier is going to be very selective. Then I would want to know what, so I want to make sure that I'm at 70.7% of whatever my total voltage is that I can be out of across my resistor. But does the frequency response chart, does that all look pretty straightforward? And yeah, this is kind of a little fun project that we did, but geez, it took us about a week to do it, but it's kind of a fun little spreadsheet. Let's see here.
Did you people put in all the numbers like manually or?
Nope. So what we did is, all we ever did was when we do a spreadsheet, all we had to do was our first row. So all we ever did was we did all our calculations for all our first rows, and then once we got those and we verified that those were all working good, then all we did is we highlighted that first row, clicked and dragged it all the way down, and we were done. So you ever have to program one row in Excel, and then after that, then you click and drag it down, it'll automatically populate all these ones here.
And it took you a week?
Well, not me, but the class. But what we did is we kind of did stuff tricky. Like here you can kind of see, so everything that's in my red column, you can see that this is actually showing it as being in scientific notation. So then what we did is we ended up, so I showed them, so we really could learn how to use Excel. So if I go ahead and I hide that row for my X of L, I'll hide that row. Then what happens was, then we actually wrote code in there so that when it looked at this number here, it could automatically convert it into a text and it give us our metric prefix. So then it would give us, here's all our ohms, and then once you got into above 1,000, then it automatically put it into kilo ohms. And that was all. So let's see if I can show you here. So let's click on one here. So here's like, so then we use if statements. You know, if it was, if E34 was greater than 1,000, or it was greater than 1,000,000, then use megaohms. If it was, if E34 was greater than 1,000, then use kiloohms. If it wasn't greater than either one, then just use your ohms. So it became a text. This became a text. It's no longer a number. It just became a text. But then we just combined the two together and made ourselves. So it looks like it's all doing everything by the metric prefixes. So we did a lot of that stuff, you know. So we really learned how to use Excel, you know. Here's all our formulas, you know, for like calculating our resonating frequency. Here's 1/2 pi, the square root of our inductor and our capacitor. So we did a lot of the formulas at the same time. And this one wasn't quite so bad. But the other one too, then we did also the frequency response curve of just our RLC circuit. I can kind of flower it on that up here. Got that handy. But it's amazing what you can, you know, what Excel can do for you and how you can graph it. So here's our frequency response curve of an RC circuit, and then we also did the phase shifts and calculated out our phase shifts for all the different. So we can actually have Excel even actually graph out our sine waves. It'll actually graph out sine waves.
When do we learn how to do that?
What's that?
When do we get to learn how to do that?
If you ever want to know, I can kind of show you. But so yeah, here. So I'm doing that to graph out a sine wave. We know that one complete cycle is 360 degrees, right? So we reference everything. This is where we used our instantaneous formula. Okay, so we knew what the value of that data point was by using our instantaneous value, and then we knew that at 0 degrees it would be at 0, but then at 90 degrees it was going to be at our peak voltage. And so we just looked at our angle, look at our degrees, put that into our instantaneous value formula, and it automatically created our graph. So there's our instantaneous value formula. It's just our voltage peak times our sine of theta. Mm-hmm. And then it automatically graphed out all those points. So we used to do that one too. So we used to do a lot of graphing on the calculator, but it would show us, all our frequency response curves. But it is kind of amazing, and so that's what we kind of do a lot of times. We just kind of go ahead and we have our Excel graph it all out, because you can see, looking at this is a lot easier than looking at data. You can see exactly what's going on. So we use Excel a lot out in the industry. All right, so let's go back to our. Let's see here.
Can you do page 2?
I was gonna try thinking about how to, because Chris was asking about if we're off frequency, can we calculate out our angles and stuff like that? And I was trying to. I know we can, because I showed you in my.
Yeah, but if the point is to get to resonating frequency, then
yeah.
we're never.
But you could go ahead and calculate out what your angle was. Once you knew what your angle was, then if you knew like at so let's see. I'm just trying to think here. So let's say that.
Well, if you're stuck at a certain frequency.
Yeah. So let's just say we knew that this is going to be our lower frequency cutoff is going to be at plus 45 degrees. And
the lower frequencies at plus 45?
That's what I was going to say.
the lower, negative. Thank you. It'd be
I'm
negative.
gonna jot that down.
Oh,
I have that
yeah.
backwards still.
Let's see, if I'm at negative 45 degrees, kind of think of it as be an easy way to
Can you use your...
You know, I guess I would, you could actually, because I know that on my spreadsheet I calculate out that 45 degrees.
Can you use your rectangular polar
You can.
picture at all?
So we know, because we know our angle, so then you would know your, let's try to think of how you can calculate out what your resonant, or what your lower frequency cutoff was by that. I know that at my 45 degrees, you know, if I use my voltage source and my angle of negative 45, I know that I can find out what my voltage is across my capacitor would be. And then I would know also what the voltage across my resistor would be at that point. I'm trying to think in my head here. I could actually calculate out my resonant or my lower frequency cutoff, because that would be what you really want to know. Is you really want to know what is this and this. But I don't know, since we already know how to do it by looking at our quality of our circuit and our calculating all our bandwidth from that, that'd probably be just the easiest way of doing it. Oh, that's one thing I was going to show you too. Let's try this here real quick. I'm going to put in let's keep that at 30. Okay, so in the book there, they talk about this too, is that, you know, it's the resistance, remember, it's figure out the quality of our circuit, it's X of L over R, right? So if I put in, so what I just did is I changed my resistor value to 150 ohms. So instead of the 47 ohms, I put in 150 ohms, so 3 times larger. And then you can see what happens now is that you can see that this gets to be wider.
Yeah.
Okay, our quality of our circuit, our bandwidth is going to get larger. So as I increase the resistance in my circuit, the wider the bandwidth. So if I have to be very selective, you know, that's what we couldn't consider our sensitivity. You know, how selective is our filter? You know, sometimes we don't want to be so selective that we can't ever stay tuned onto that frequency. So we do want to have some bandwidth, but we don't want to have it so wide that we're picking up other radio stations on the other side of our bandwidth. So you have to be careful of the resistance of your circuit and the quality of your inductor. So it wouldn't matter if I changed the quality of my inductor or my quality of my resistor. If I had a really bad quality, if I had that as, let's say, we'll double that, say 60 ohms. Then my bandwidth again got wider, and this is, you know, so this ended up getting a little bit wider. So we're really going to be very selective on making sure that we don't have too much resistance into our circuit, especially if we're going into another device or something like that. You know, we want to make sure that we're loading it down properly, and that's where we're going to start talking about P's matching and stuff like that when we get into transformers. All right. I think that's about, if you can remember all that, then you'll be doing good in Dan's class. That'll be, you know, those are all things to remember.
I don't see how the resistance of the windings would affect the bandwidth. Isn't that the resistor value? I don't...
Nope.
We kind of ignored the resistance of the windings.
No, we didn't.
Schematics, we didn't?
Nope. Because remember, we calculated out RT.
Yeah, right, okay.
Yep, and so we included the resistance of the winding and the resistance of those
Since you
things.
take your outputs across the resistor, that resistance will be within the inductor.
If I take, well, that's why we're losing, because remember that my voltage across my so here, let's,
I just figured you'd lose bandwidth if the resistance was outside of your outputs.
if this was ideal, if that was ideal and I didn't have any resistance of the windings,
Yeah.
my voltage across my resistor on my output would be equal to my source voltage.
Right.
Yep. But since I have the resistance of the windings,
Yeah.
a portion of that voltage is going to be dropped across that winding, which is right here.
Right.
So I'm going to lose, about 40 millivolts across just that inductor, which is unmeasurable. I can't measure it. If I measure it, I'm going to measure the voltage drop across the inductor, not the resistance.
That's why I was wondering why your bandwidth would increase. Because you take the outputs across your resistor, not the...
Right, but remember that the source voltage doesn't see two separate resistors.
Okay.
It only sees the total resistance of the circuit.
Right.
And so what I actually have is, basically what I got is a voltage divider. Here's the resistance of the winding, and then here's my resistance of my actual resistor.
Right.
So it's going to just do a voltage drop across those two.
Okay.
So even though the total voltage across that resistance is going to equal my voltage source,
Yeah.
but since I'm only measuring across the resistance of the resistor, or the voltage across the resistor, then I'm only going to get that certain amount of voltage.
Alright.
The other remainder is going to drop across the resistance of the winding.
Yeah.
Does that make sense?
Yeah, just because the voltage would be less across the resistor, I figured your bandwidth would decrease because more voltage is dropped outside of your outputs. So you lose voltage outside of your outputs.
Yep, I'm going to lose all. Yep, I am. I only got to 60 millivolts. I didn't get to my source.
I was just confused. I figured you'd lose bandwidth
Yeah.
because of that.
Yeah, and so when this thing is running at resonating frequency, it looks like this inductor and capacitor are directly dead short. So my equivalent circuit for this circuit then is basically so here's my V out and my V in. That's what my equivalent circuit looks like at resonating frequency. It doesn't even see, the power supply doesn't even see that the inductor and the capacitor is even in the circuit. It doesn't even see it. It's not there, it's non-existent. So the only thing that this power supply sees is the resistance, the 30 ohm resistor of the resistance of the winding, and the 47 ohms of the resistor. And so what I'm doing is I'm just making myself a voltage divider, and that voltage in, my 100 millivolts AC, portion of it's dropping across the resistance of the winding, and the remainder is dropping across the resistor. So that's exactly what the power supply sees, is just those two resistances. And then in theory, all it's really seen is it's actually only seeing one resistor. The power supply only sees it as being one resistor.
Right.
Yeah. It doesn't know that it's separated up. All right. Any other questions about that? About the series one? Let's take a look at. I don't think I have any parallel circuits. Sure I don't. But we could do the one right in the book though, and that'll save you some lab time. Let's see what they're using for. See how deep they get into it. They don't even get into. Yeah, you don't have to do your. You have to do your vectors on the parallel one. That one's pretty straightforward. But let's see. those get to be, some of those ones get to be pretty complex by just changing your circuits up a little bit. Yeah, maybe. Instead of calculating it all out, since we don't need to do that in our lab, let's some of this stuff we just the big formula that you really need to know is that your resonating frequency and calculating that calculating out your resonating frequency. But understanding, recognizing filters and stuff is the big one. So let's just see if there's one that